Okay, final lessons, grade 11 of your entire Chem 20 course. This is very exciting. It's going to be in 3 parts. Hopefully we will have time to do a lab before we get into our review wrap-up. But we're going to be looking at acid-base titrations. We have kind of already talked about this. We've looked at the indicator portion of it. But we're going to be looking at titrations, and I'm really hoping that we can get to do a lab. So when we do solution stoichiometry, so solution means that we're working with molar concentration. Sometimes we don't have enough information that we can actually solve the problem on paper. So for example, 10 milliliters of acetic acid reacts with 0.202 moles of sodium hydroxide solution. What's the concentration of acetic acid? As you can see here, we're missing, this is what we're looking for. This is acetic acid, and this is sodium hydroxide. But we don't have the volume because we need to be able to go from what's given to us multiplied by a volume. This is step 3. Then we need to multiply by mole ratio, which is step 4. And then we would need to multiply by, or divide by, the volume to get concentration, which is step number 5. And you can follow through with that on the chart that was given to you. But we're missing this piece right here. In order to find out how much volume of sodium hydroxide was used, an experiment called a titration is what is used. So a titration is a procedure or an experiment used to find the volume of substances so that you can calculate concentrations. The first thing that you have to do is you have to standardize your solutions. So it's when a solution of known concentration, so this is something that we know with confidence, and we call it a standard solution, is reacted with a solution of unknown concentration. So both strong acids and bases need to be standardized because their concentrations will change over time. Standardized. Okay. A solution called the titrant is transferred from a precisely marked tube called a burette. We spell this wrong. I've seen it spelled this way. I've also seen it spelled this way. To a flask that contains our sample and an acid-base indicator. So we looked at a couple of those when we were figuring out what kind of indicators to use. We looked at phenolphthalein when we did our experiment. We had phenolphthalein paper. We had red cabbage indicator. We had universal pH paper. Those are all different forms of indicators. But when we're doing a titration, we would actually add the red cabbage indicator. We would add a couple drops of a liquid indicator to our solution, and then when we did the experiment, we would be looking for a specific color change. I'm going to show you a picture here. So this long tube with graduated markings and this, what we call this is a stopcock at the bottom, this is our burette. Oops, still spelled it wrong. And this part here is what we call an Erlenmeyer flask. And our sample goes in here. So this is our unknown concentration. Excuse me. And this is our standard. And this is our known concentration. So if you want to draw that picture out, you would just pause the video and draw it out and go back. An indicator. So we've talked about those: methyl orange, bromophenol blue, phenolphthalein, red cabbage indicator, pH paper. We use those because there's a sudden change in color. Which indicates that the reaction has gone to completion. So when we're looking at phenolphthalein, we look at our data booklet on the indicator page, which is the second to the last page. Phenolphthalein has an indicator range of 8.2 to 10. If I'm coming from a position of being acidic, I'm going to be colorless, and then as soon as I hit that basic, as soon as my reaction is completed, my indicator will turn pink. And then we know that we're done. We don't need to keep going further ahead. So when we are done, an endpoint is the point where the titrant reacts completely. With the sample. Okay. An equivalence point, so sometimes these words get interchanged, is the volume needed to get to the end point. It's the amount of standard that we added to make the reaction go to completion. We always do 3 trials, always. Statistically, when you get up into higher math, you will see that statistics comes really big into play. You always need a minimum of 3 trials, and your results have to be within 0.020 mils of each other to ensure that they're accurate. So if you had a sample and this was volume added, and you had 10.7, and you had 10.85, and you had 11. These two here are within the 0.2. This is 0.15. These two here are within 0.15, but overall, this is 0.3 mils. And so we would not be able to use either the 11, and we would use the 10.7 and the 10.85, or we would not use the 10.7 and we would use the 10.85 and the 11, because our data has to be within this 0.20 milliliters difference. I will upload a video for you to watch about how a titration occurs, but hopefully we will get to do this in person. So if I was to do a lab, I would have my burette, I would have my flask. I'm just going to draw a little miniature picture here. So here's my burette, and here's my flask with my sample in it. Okay, this is all graduated markings. So it says a 10 ml sample, so there's 10 milliliters in here, was titrated with a standardized solution. So in here is sodium hydroxide, and in here is HCl. And I know that my concentration is 0.685 moles per liter of sodium hydroxide. I put a couple drops of bromoflammable blue, so I'll just put a couple drops in bromoflammable blue. I would have swirled it and made the whole solution a certain color. It would have been yellow, and I add in little bits of sodium hydroxide, and then all of a sudden it goes from yellow to blue. I stop adding sodium hydroxide at this point, and I write down the volume. So if I was to do this titration, what I would have, acetic acid, hydrochloric acid. I would have, let's see if I can find this. Let's say my start, when I read, my initial volume will be up here. So let's say I started at 0.00 and I added 10.6 milliliters. The volume of sodium hydroxide that I added was 10.6 milliliters, and my color went to blue. Okay, when I then add, when I then go and do my second trial, and I start with 10.6 milliliters because I'm going to start where I ended off. So now I've moved down my burette and I'm sitting right about here now. And I add, let's go 18.8 milliliters. My volume of sodium hydroxide that I added is 8.2 milliliters. And this is a very faint blue. It's not green. It's very important that you recognize that we didn't stop when it went green, but it's not a real dark blue like what we got here. Okay, they don't have them. They're not 0.2 milliliters apart. So I start again. I start at 18.8 milliliters because I'm just going to start where I left off. And I get to 26.8 milliliters. My new volume is 8.0 milliliters. And again, I have a very faint blue color. In my third attempt, because you have to do 3 trials, in my third attempt, I'm going to start at 26.8 milliliters because now I'm here on my burette. Okay, and I'm going to add, or I end up adding 34.9 milliliters. Or that's where I stopped. I added a total of 8.1 milliliters, and I still have a faint blue coloring. Okay, so here are my 3 trials that from the lowest to the highest value, I'm within that 0.20 milliliters. This one we're going to get rid of. I wasn't paying attention. I was talking to Jennifer and I got sidetracked, and one thing led to another. We all know how that goes. Okay. The first thing I need to do is I need to average how much volume I actually use. So I'm going to go 8.2 plus 8.0 plus 8.1, and I'm going to divide it by the number of trials that I did, which was 3. And I get 24.3 divided by 3, which means I used an average of 8.1 milliliters of titrate for my standardized solution. Now that I've done that, I can go back and I can calculate out the concentration of hydrochloric acid, because this is my reaction. I took hydrochloric acid and I reacted it with sodium hydroxide, and I would have gotten sodium chloride and water. I had 0.685 moles per liter of this. I had a 10 ml sample of hydrochloric acid. I'm looking for my concentration, and I see here that I need my volume. Well, from my experiment, I used 8.1 mils, which we know there's 1,000 mils in 1 liter. So I used my calculator, so I'm smart, 0.0081 liters. Now I can go through the stoichiometry process. Step 1, balance an equation. Step 2, write down our given information. Step 3, find the moles of our given. So 0.685 moles per liter of sodium hydroxide multiplied by 0.0081 liters. I'm now in moles of hydroxide. Step 3. Step 4 is my mole ratio of want over have. I want hydrochloric. I have sodium hydroxide. And we see in the equation that it's 1:1. And then it's asking me to calculate the concentration. And concentration, we know, is moles per volume. So in step number 5, I'm going to have, where am I at? Liters, sodium hydroxide. I'm in moles of hydrochloric acid. So I'm going to divide it by my sample. And 10 mils into a liter is 0.01 liters. 0.01 liters. And I would get 685 multiplied by 0.0081 times 1 divided by 1 times 1 divided by 0.01. I get 0.55485 moles per liter, but I'm going by significant digits and I need 3. So 0.555 moles per liter of hydrochloric acid. Okay, that's how we're going to solve these kinds of questions. So you're going to work on page 22 in your workbook. Remembering to pause your video here because we're going to move on to the second portion of this section when you're done your questions. Okay, when we add the titrant or the standard into our sample, we can actually plot that reaction as a titration curve. And I really hope that we get to do this lab because we have the equipment where the computer will draw the curve for you, and it's really quite interesting to watch it evolve. If we're going to plot the titration curves, we're going to go pH versus the volume of titrant added. And we're going to call this, very simple, a pH titration curve. Nothing fancy. Titration curves are S-shaped, and they are when a strong Monoprotic, meaning that it only has one hydrogen to release, is titrated with a strong monoprotic base. The equivalence point will always have a pH of 7 when we're at 25 degrees Celsius. The first point on the curve is always the pH of the sample. So it's where we're starting. The pH changes very gradually, and we call this the buffer region. So what's happening is you're titrating a strong acid or a strong base against a sample, and it's taking quite a while for that hydrogen to want to get ready to leave. Okay? Once we get closer to that endpoint, the pH changes quite rapidly. And when you watch the demo of the video of the titration, you can see that they add drops fairly quickly and then they slow down the drops. And that's when the pH really starts to do a shift. And you want to make sure you go slow. And so when you over titrate, it's asymptomatic or asymptotic, meaning that it doesn't change the graph. It just becomes what's left of the titrant. So if we were to look at a strong acid with a strong base, I'm going to draw a dotted line. See if I can get this work. So in my burette, right, this is where my titrant is. And this is where my sample is. So my volume of my titrant, it's going to start down low. I'm going to start with a strong acid. This is the acid. Nope. This is the base. This is the acid, because I just finished telling you the first point on the curve is always the pH of the sample. My sample is acid because I'm starting below 7. What you're going to see is you're going to see a very gradual change in pH, and then all of a sudden you're going to see a radical shift and then a leveling off because you're adding base. Now your solution is mostly base, and here your solution is mostly acid. And right here is your equivalence point. Okay? Right here, strong monoprotic acid is titrated with a strong monoprotic base. The equivalence point will always have a pH of 7. If I did the opposite, so in my burette, I have, this is my sample. I'm titrating a strong base with a strong acid. My pH is going to start here, a strong base. Then I'm going to slowly add acid into my sample, and I'm going to see this. And then a rapid change, and then a gradual tailing off. And again, this is my equivalence point. This part here is my buffer region. Right before it starts to do the downward curve. This part here is not a buffer region. This is just excess titrant. That's this asymptotic to the pH of the titrant. So this part here is my buffer region. And this part here is just excess base. Okay. All right. No questions, because we're going to do a lab. Hopefully we do a lab. Let's look at part C for indicators. Easy peasy, because we've already looked at indicators. pH meters are how we use this to measure the pH as the change is happening, and it's the most convenient indicator. We're not waiting for something to change. An indicator should change color immediately when the endpoint is reached. So when we're working with samples, we'll be working with a phenolphthalein indicator as well as a pH probe so that you can see the two happening together. But when you're using that indicator, you're going to go clear, 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 pink. It should be immediate. All right. The pH of the endpoint should fall within the range of the indicator. And how do you know which indicator to choose? Well, you're going to do your reaction. You're going to write out a balanced equation. I'm reacting sodium chloride or sodium hydroxide with acetic acid, strong base, weak acid. I know that acetic acid sits around a 4, whereas sodium hydroxide sits around a 13. So I'm going to want something that's going to show me a color change as it gets close to being a base. And that's where phenolphthalein is a really common indicator because it's clear for anything below 8.2 and it's pink for anything above a pH of 10. If you suspect that your pH is going to change right around the 8 region, then you would need to pick a different indicator. And that's why we have indicator charts to make our life easy. All right, no calculations for this. Hip hip hooray. And be prepared to do a final lab.